Welcome to the Deep Dive, where we get into some really fascinating topics. And today, we're going to be diving into a patent for a self-contained ion-powered aircraft.
Yeah, we're going to be looking at patent number 10,119,527B2. Filed by Ethan Krauss back in 2015.
So this patent goes beyond just the basic principles of how aircraft work and really gets into the technical nitty-gritty
Right.
of a design that specifically aims to solve a challenge that has plagued ion-powered flight for I don't know how long.
Yeah, so the problem that Krauss is really trying to tackle here is this inability of previous Ionocraft designs to actually lift their own power source, which has kind of limited them to just these brief little hovers instead of, sustained flights.
And so Krauss's patent claims to overcome this with a number of innovations that he details across four key components: the collector assembly, emitter assembly, the power supply, and the control circuit.
Yeah, each one of those plays a really critical role in generating and controlling the ion wind effect, which is the principle behind this type of propulsion.
Okay, so let's start with the collector assembly,
Okay.
which is described as a lightweight conductive structure that is shaped to evenly distribute electrical energy and minimize any kind of energy loss.
And Krauss really stresses the importance of the shapes of these collectors.
Right.
He favors concentric or spiral designs because they maximize the strength-to-weight ratio,
Okay.
and it really helps to minimize warping.
Now, does he give any specific examples in the patent of what this might look like?
He does. He gives a couple.
Okay.
So one is multiple hexagonal elements that are formed into kind of a teardrop shape.
Okay.
And he suggests using things like carbon fiber veil or aluminized plastic.
Okay, so lightweight but strong.
Exactly.
Right.
And then another example he gives is a single hexagonal spiral shape that's crafted from this really, really thin aluminized polyester film.
Wow.
It's only 3 microns thick. So he's really focused on keeping the weight down, but also maintaining the structural integrity of this collector.
So that's the collector assembly.
Right.
Now, what about the emitter assembly?
Okay, so this is the part where the ions are emitted to generate that thrust. And it's described as these thin conductive wires that are less than 5 microns in diameter, suspended above the collector assembly.
Okay.
Again, weight is really key here.
Right.
Keeping it as light as possible.
Now, what I find really interesting is that he positions the emitter a significant distance away from the collector, like 6 to 8 inches.
Yeah, you would think you'd want them closer together.
Right. I would think efficiency would dictate a smaller gap. But he argues that this actually enhances efficiency.
Right.
He doesn't really explain it in the patent. But
he doesn't really go into detail about the physics.
Yeah.
But it's definitely an interesting choice.
Now, does he mention anything about steering? Because obviously, if you're going to have a craft that flies, it has to be able to be steered.
Yeah, so he actually arranges the emitter wires in 4 quadrants.
Okay.
And this configuration allows for steering by controlling the voltage to each of those quadrants.
Oh, so you can create differential thrust
Exactly.
to steer it.
Yeah, maneuverability.
Okay, so now let's talk about the power supply.
Okay.
This is really the heart of it.
Yeah.
Because this is what generates the high voltage.
Right, we're talking about 30,000 volts.
30,000 volts needed for this ion propulsion.
Yeah, and it's pretty complex.
Okay, so walk me through it.
So he starts with lightweight lithium polymer batteries, which are known for their high discharge rate.
Okay.
And then he uses a modified Royer circuit, which acts as an inverter to convert that direct current from the battery into alternating current.
Okay, and then where does it go from there?
All right, so then it goes into a low-profile drum-shaped resonant transformer, which steps up the voltage to about 3,000 volts.
3,000, okay.
But we need to get to 30,000.
Right.
So to do that, he uses a modified Cockcroft-Walton voltage multiplier.
Okay.
And that not only increases the voltage, but it also reduces the current.
Which increases the efficiency.
Exactly.
Okay, so he's really thought this through.
Yeah, and this modified Cockcroft-Walton multiplier is a really good example of how detailed he gets.
Okay.
He actually talks about optimizing the placement of capacitors and diodes to minimize the weight and the power loss.
Okay.
And he even talks about the shape of the diode paths.
So really, really detail-oriented.
Absolutely.
Okay, so we've got the collector assembly.
Right.
We've got the emitter assembly. We've got the power supply.
Yeah.
Now, what about the control circuit?
Okay, so the control circuit, this is what manages the power distribution.
Okay.
It's what enables the steering and the stabilization of the aircraft.
So how does it do that?
So he mentions using a receiver to interpret user commands.
Okay.
And then there are variable resistors in each quadrant of that emitter assembly.
Okay.
So that you can adjust the voltage and control the lifts.
Right, which allows for the steering.
Exactly.
Now, what about stability? Because obviously wind and things like that could really affect a craft of this size.
Absolutely. And he addresses that by suggesting the use of optical flow sensors and gyroscopic stabilization to counteract that wind.
Oh, so it can actually self-correct.
Exactly.
Go ahead.
And maintain a stable flight path.
So we're talking about a pretty complex system here.
Yeah, it's a lot of technical intricacies.
But the goal is clear.
The goal is clear. It's to generate and control this powerful ion wind for propulsion,
right?
But at the same time, address those weight limitations that have been such a problem for these Ionocraft designs in the past.
Right.
That's really been the stumbling block.
Okay, so we've kind of gone over the core components of Krauss's design here.
Right.
But what really makes this patent stand out are the key innovations that he claims make unassisted flight possible.
He really highlights 4 major innovations.
Okay, let's hear them.
Okay, so the first one is the unique shape of the collector and emitter assemblies.
Right, which we touched on.
Yeah. Which we talked about, yeah.
And those are designed to distribute that electrical energy evenly and minimize energy loss.
Right, for the most efficient thrust possible.
Okay, what's the second one?
The second one is that increased distance between the emitter and the collector.
Right.
Which is kind of counterintuitive.
It is, yeah.
But he argues that it improves efficiency.
Okay, number 3.
Number 3 is the emphasis on a low current, high voltage system.
Okay.
And that minimizes energy loss through what's called joule heating,
right,
which is a big problem in high voltage systems.
Right.
And then finally, the fourth one is that modified Cockcroft-Walton voltage multiplier.
Right.
With that really optimized design and component placement.
Yeah, reducing weight and power loss.
Exactly.
So these 4 innovations together form the basis of his claim to have achieved this self-contained ion-powered aircraft design that can lift its own weight.
A feat that nobody else has been able to achieve in this field so far.
Right. And that's the real breakthrough here, potentially.
It could be, yeah.
But the patent doesn't just stop at outlining the fundamentals.
No, it goes beyond that.
He also goes into some potential applications of this technology.
He does.
What does he say?
So he suggests that this design, with a few adaptations, could potentially function outside of the Earth's atmosphere.
So we're talking about a spacecraft.
We're talking about an ion-powered spacecraft.
Wow.
Which is pretty amazing.
That is pretty amazing.
Yeah.
So how would it achieve that?
He proposes using either onboard propellant or expelling high-voltage electrons to achieve propulsion in a vacuum.
So he's really thinking outside the box here.
He really is.
Now, does he talk about any other, far-out ideas?
He does. He talks about creating even more powerful versions of this aircraft using what he calls megavolt towers.
Megavolt towers.
And these would generate incredibly high voltages, potentially in the megavolt range.
Wow.
Using sub-nanosecond pulses to dramatically increase lift.
So now we're getting into science fiction territory.
It sounds like it, but he's clearly a forward thinker. And he's really pushing the boundaries of what might be possible with this technology.
Right. So he's combining the technical depth with some really interesting visionary thinking.
Absolutely. And that's what makes this patent so compelling.
It's not just a blueprint for an aircraft.
It's a window into the future.
It really is.
A future where ion propulsion could completely redefine our relationship with the sky and beyond.
Now, we've covered a lot of ground in this initial exploration.
We have.
Of Krauss's patent.
Right.
But there's still a lot more to unpack.
Yeah.
I think we need to dive a little deeper.
I agree.
Into some of the specific design choices and technical details that really highlight his innovative approach.
Yeah. Let's get into the nitty-gritty.
Let's do it.
All right. One of the things that really jumps out at me when I'm reading this patent is Krauss's just obsession with efficiency.
Yeah, it's everywhere.
It permeates every aspect of this design. Like he is laser focused on minimizing energy loss at every single stage.
Yeah, you can see it in the material choices, the component placement, even the shape of the electrical pathways.
Absolutely. It's clear that he's not just throwing components together. He's carefully considering every single aspect of their design and their placement to optimize the system as a whole.
I mean, one example that really jumped out at me was his description of the modified Cockcroft-Walton voltage multiplier.
Yeah.
He talks about how he actually curved the diode paths to reduce power loss.
Yeah.
Without having to add extra insulation. which is pretty ingenious.
It really is. It's a testament to his problem-solving abilities.
Absolutely. And then you see it again in the power supply itself.
Right.
He specifically chooses lightweight lithium polymer batteries, which are known for their high discharge rate.
Which is really important when you're talking about providing the power needed for ion propulsion.
Exactly.
Yeah.
And he doesn't just stop there. He goes on to describe how he's using a resonant transformer driven in what he calls strike mode to achieve a high voltage output with a relatively low current, which again minimizes that energy loss due to joule heating.
Yeah, that's a major challenge in these high voltage systems.
Right, and then we get to this whole thing about the distance between the emitter and the collector.
Right, a larger gap.
Which is counterintuitive.
It really is. You would think you'd want them as close as possible.
I know, to maximize the efficiency.
But he insists that it actually works better this way.
He does, and while he doesn't really explain the physics behind it...
No, he kind of glosses over that.
He does. But it's obvious that he's arrived at this conclusion through a lot of research and experimentation and analysis.
Right, he's done his homework.
He has. And it's just a reminder that even in a field like aviation where we think we know everything,
right,
there's always room for unconventional thinking.
Absolutely.
And new approaches.
And Krauss definitely isn't afraid to push the boundaries. I mean,
he's not.
He even talks about adapting this design to operate outside of the atmosphere.
Right, we talked about that ion-powered spacecraft.
Which is just mind-blowing.
It is, and he suggests using either onboard propellant or expelling high-voltage electrons to achieve propulsion in the vacuum of space.
Which is pretty amazing when you think about it.
It is, and then he goes even further. He starts talking about these megavolt towers.
Oh, yeah?
To generate incredibly high voltages.
Potentially in the megavolt range.
Which is just insane.
It is, but he's using these sub-nanosecond pulses to dramatically increase lift.
It's like something out of a science fiction movie.
It does sound pretty futuristic.
It does, but it really highlights his ambition.
Right.
And his willingness to push the boundaries of what's possible with this technology.
He's a real visionary.
He is. So Krauss is clearly a big thinker.
Yeah.
And his patent really reflects that.
It does. It showcases his ingenuity and his willingness to challenge the status quo.
But as with any new technology,
right,
there are practical considerations.
Oh, absolutely.
Can this design be scaled up to create larger, more practical aircraft?
That's a big question.
What about the safety implications of working with these incredibly high voltages?
That's another big one.
And what about the environmental impact?
Right. We have to consider all of those things.
These are all really important questions.
They are.
That need to be addressed as this technology continues to develop.
Absolutely. But one thing is for sure.
What's that?
Krauss's patent has definitely started a very interesting conversation.
It has.
About the future of aviation.
And the potential of ion propulsion.
It's definitely a technology to watch.
So let's dive into some of those specific design choices that Krauss highlights in the patent.
Okay.
For instance, he talks a lot about the importance of material selection.
Right, in achieving that lightness and structural integrity.
Exactly. He talks about using carbon fiber veil and aluminized plastic for the collector assembly.
Yeah, those are great materials for that because they've got that high strength to weight ratio.
Right. And then for the emitter assembly, he talks about using these thin annealed nylon threads to support the emitter wires.
Again, minimizing that weight.
Right. And he even mentions incorporating boron filaments into the frame structure.
Right, because boron's a poor electrical conductor.
Which helps to prevent interference with the collector surfaces.
Exactly. It's really interesting how he's thought of everything.
He has, it seems like every material choice has been very carefully considered to optimize performance while minimizing weight.
Right, because weight is the enemy when you're trying to achieve sustained flight.
Exactly. And this attention to detail extends to the electrical components as well.
Oh, absolutely.
He talks about modifying existing circuits and components to meet the specific demands of his ion-powered aircraft.
He talks about modifying a commercially available inverter, a VXA302.
Okay.
And he removes unnecessary parts, and he adds better insulated windings to handle the higher voltages.
Right, because he's dealing with a lot more voltage than a typical inverter.
Exactly, and he's not afraid to get his hands dirty and actually modify these things himself.
No, he's not. He's a tinkerer.
He is.
And then he goes on to describe how he modified a Royer circuit.
Right.
By incorporating a larger inductor to improve efficiency.
Which is another clever little tweak.
It is. And then, of course, there are his alterations to the Cockcroft-Walton voltage multiplier.
Right, which we talked about earlier.
Which are all aimed at reducing power loss and enhancing overall performance.
It's really impressive how much thought he's put into every single detail.
It is. So he's not just throwing out these theoretical concepts.
No.
He's actually taking existing technologies and refining them
Right.
to meet the very specific demands of his ion-powered aircraft.
It's a very hands-on approach to innovation.
It is, and you see that in his approach to the distance between the emitter and the collector.
Right. The larger gap.
Which, again, is counterintuitive.
It is, but he insists that it's more efficient.
He does. And while he doesn't really go into the physics of why that is,
no,
it's clear that he's done his research.
He has.
And he's arrived at this conclusion through experimentation and analysis.
Right. He's not just guessing.
He's not. And it's a good reminder that sometimes you have to challenge those conventional assumptions.
Absolutely.
And explore those unconventional solutions.
Because you never know what you might find.
Exactly. And Krauss clearly isn't afraid to do that.
No, he's not.
I mean, he's talking about an ion-powered spacecraft.
Right.
Which is pretty out there.
It is, but it's exciting.
It is, and he's proposing using onboard propellant or expelling high-voltage electrons to achieve propulsion in a vacuum.
Which is just mind-blowing.
It is. So he's not just thinking about flying here on Earth.
No, he's thinking about flying anywhere.
He is.
He's thinking about the future of space exploration.
And then there's his idea for megavolt towers.
Yeah.
To generate those incredibly high voltages.
Using those sub-nanosecond pulses.
It's like something out of a science fiction novel.
It is.
But it shows his ambition.
Absolutely.
And his willingness to push the boundaries of what we think is possible.
He's not afraid to dream big.
So Krauss is a visionary.
He is.
But his patent isn't just about tie-in-the-sky ideas.
No.
He's also got a very solid grasp of the technical details.
He does. He's an engineer.
He is.
He knows what he's doing.
And that's what makes this patent so fascinating.
It's the combination of those two things.
It is.
The vision and the technical expertise.
But of course, the big question is,
yeah,
did this thing ever actually fly?
Right. Did he build it? Did it work?
Unfortunately, the patent doesn't really answer that question.
No, it doesn't give us any data.
It doesn't. And publicly available information about Krauss's work beyond the patent is pretty limited.
It is. So we're left wondering.
We are.
Did he actually manage to build this thing and make it fly?
Right, because the patent itself, while very detailed and comprehensive,
yeah,
doesn't really provide any evidence of its practical implementation.
Right, it's a blueprint.
It is.
But we don't know if it ever became a reality.
So there's this gap.
Yeah.
Between the theoretical design and the real-world testing.
Which is common with these cutting-edge technologies.
It is, but it makes you wonder.
It does.
Imagine seeing this thing actually take flight.
It would be amazing.
It would.
To see this silent, emission-free aircraft soaring through the sky powered by nothing but ion wind.
It would be a sight to behold.
It would.
And Krauss's patent is a step towards that future.
It is a very important step.
So while we don't know for sure if his aircraft ever flew,
right,
his work has definitely contributed to the advancement of this technology.
Absolutely.
And sparked a lot of interest in the potential of ion propulsion.
It has. It's a very exciting field.
It is, and it'll be interesting to see where it goes from here.
I agree. So let's move on now and talk about some of the broader implications of Krauss's work.
Okay.
What could this technology mean for the future of aviation?
Right. What are the potential benefits and the challenges?
And what are the ethical considerations?
Let's dive in.
All right.
When we talk about any new technology, one of the first things we have to consider is what kind of impact it's going to have on the environment.
And especially with aviation, with its reliance on fossil fuels and the contribution to greenhouse gas emissions, this is a really important consideration.
Krauss's design seems to offer a way towards a more sustainable form of aviation, one that could potentially really cut down on or even eliminate these harmful emissions.
Yeah, because you don't have combustion with ion propulsion, there's no release of those pollutants into the atmosphere, like carbon dioxide, nitrogen oxides.
Right, and that could have a really significant impact on air quality, especially around airports, which often have, higher levels of pollution.
And then there's the reduction in greenhouse gas emissions, which is important when we're thinking about climate change.
It is. But even if you eliminate those direct emissions from the aircraft themselves, we still have to consider the overall environmental impact.
Right. The production of those materials and components that are used in the aircraft, and then the energy that it takes to manufacture and operate them, all of that has to be factored in.
Right. So you need a full life cycle assessment.
Exactly. To really understand the technology's environmental footprint and figure out if there are ways to make it even better.
Now, what about the economic impact of something like this?
Well, there's the potential for new industries and job opportunities as this technology develops.
Right. And a shift toward a more sustainable form of aviation could attract investment from governments and organizations that are trying to address climate change.
Absolutely. But there are going to be challenges, too.
Like what?
Well, initially, the costs of developing and manufacturing these aircraft are likely to be pretty high,
Right.
which could make them less accessible in the early stages.
And you'd also need new infrastructure like charging stations at airports.
Exactly. And then there's the potential for disruption of existing industries and job markets as we transition to a new technology.
Now let's talk about the societal implications of ion-powered aircraft.
Well, quieter aircraft would really improve the quality of life for people who live near airports.
Right. Less noise pollution and the health problems that come with it.
Exactly, and it could create more harmonious urban environments, maybe even allow for airports to be built closer to city centers.
And then there's the increased accessibility that quieter and potentially more affordable aircraft could bring.
Yeah, which could really help to connect people and cultures around the world.
But we also have to think about the potential downsides of increased air travel.
Like the strain on tourism infrastructure and the environmental impact.
So, as with any new technology, we need to approach this with a balanced perspective, looking at both the benefits and the risks.
Exactly. And we need to have those conversations between scientists, engineers, policymakers, and the public.
Right, to make sure that this technology is developed and implemented in a way that benefits everyone.
Absolutely.
So Daniel Krauss's patent for a self-contained ion-powered aircraft has really opened up this whole discussion about the future of aviation.
It has, and while we don't know for sure if his design will ever be practical or what the ultimate impact will be, it's a great example of human ingenuity and the potential for innovation to change the world.
And that's what we're all about here on The Deep Dive, exploring those unexpected and intriguing ideas that could shape our future.
Exactly. So thank you for joining us, and we'll see you next time for another Deep Dive.